I want to talk to you about standard deviation. The best way to understand standard deviation is to start to appreciate that there's something really very wrong with variance. So I want to look at the variance computation and I want to try to convince you that I should have a complaint here. There should be something about this computation that doesn't quite make sense. Now, I advertised that the variance was a measurement of how spread out the data is, and it is. If the data is very spread out, you'll get a very large number for the variance. And if the data is very tightly clustered, you'll get a very small number for the variance. The reason is not hard to figure out. If the data is tightly clustered, these numbers will all be small because they are the data values compared to the mean, and the difference between them will be small. And then the squares, of course, will also be small. If the data is really very spread out, lots of data values will be very far from the mean. These numbers will be large positive or large negative, and their squares will be large. So the variance really does measure how spread out the data is. What's wrong with it? Well, units. What's wrong with it is it has the wrong units. So in order to appreciate this, I want to take this data and I want to presume that this data means something. So let's imagine that we're botanists and we're studying plants and we're planting some seedlings and we're measuring how high they grow. And these are the heights of these plants in inches, okay? So the important thing here is these numbers now have some meaning, and the meaning has some unit associated to it, which is inches. So these are the heights of 10 plants in inches. So, okay, this average is an average height in inches, and it makes perfect sense to explain what 6 inches means, right? First of all, the average has a unit of inches, and we can say in a very natural way that these plants, even though only one of them is actually 6 inches, these plants are on average 6 inches tall. That makes perfect sense, right? So there's nothing wrong with the mean. The mean makes sense. It has the same units as the original data. There's something really wrong with the variance. So what units will we get on the variance? This is not so obvious. So let's sort this out. All of these values are in inches. The x bar value, the mean, is in inches. When we subtract an inch value minus another inch value, we'll get inches. So these numbers here will be in units of inches. Then we're going to square them. If we take numbers whose units are inches and we square them, the units on this will be square inches. So this will be 25 square inches, 4 square inches, 4 square inches. I don't know how to interpret that, but this is still the middle of the computation, so I'm not so worried about it. I add up a whole bunch of numbers, each of which represents square inches, and that's going to be 108 square inches. Then I have one more computation, and I divide by the numeral 9. Now that 9 is a count on how many plants there were. It's actually one less than that count, but it's a count. And therefore, it doesn't actually have units. And so we're going to take 108 square inches, and we're going to divide by 9, simple numeral 9, and we're going to get 12 square inches. So the variance for these heights of these plants is actually 12 square inches. And now you should be scratching your head thinking, what on earth does that even mean, right? It's supposed to be a measurement of how much the plants vary, and the measurement is to, oh, how much do they vary? You want to know how variable the plants' heights are? Oh, 12 square inches. We're thinking, what 12 square inches? What is that? That sounds like an area, and there's nothing about area even being measured here. So the units on the variance, they don't actually make any sense, okay? Just to make this point nice and clear, let's go through it again with a different unit. Let's say instead of being the heights of plants, these are quiz scores, right? Maybe we have a quiz and it's out of 10 points, and well, I guess these quiz scores aren't very good, but oh well. So these are quiz scores for 10 students, and the units are points, right? These are like how many points you earn on your quiz. So xi is in points, x bar is in points. We subtract them, this will be units of points. Square them, these will be square points. I don't even know what a square point is. It doesn't sound like anything I can make sense of, but okay, it's going to be in square points. This calculation is square points, whatever that means. And then we divide by 9. The variance is 12 square points, which makes even less sense. If these are ages in years, then these are ages in years. These are square years. So the units on this, years. Units on this, square years. I don't know what square years are, but that's what the unit is. Then we get 108 square years. We divide by a simple number, 9, and we end up with 12 square years. So if these are ages in years, then the variance is 12 square years. And I don't know what sense to make of that, right? If these are a bunch of kids and these are their ages, and to say the average age is 6 years, I know what that means. I can make sense of it. If I say the variance of the ages is 12 square years, I don't even know what a square year measures. And so this is what's wrong with the variance. It is a measurement of how spread out the data is, but it gives you a measurement in a unit that we simply can't make any sense of, which leads us to the standard deviation in a very obvious way. So the idea is, now I'm going to retitle this, the standard deviation. It's not going to fit. The standard deviation of a data series. And so here's what we do to calculate the standard deviation. First, we calculate the variance, and then we take the square root of it. Okay? And the result of taking the square root of it, we have a symbol for that. And I'll tell you what symbol we write. Standard deviation formula. We take the symbol for the variance, we take the square root of it. Now, you could see that it was a little bit weird, but I decided to call the variance s squared, or we as a culture decided to call the variance s squared. So when we take the square root of that, gosh, what should we call it? We're simply going to call it s. So s is actually the standard deviation. S squared comes first, right? From the mathematics of the formula, we would normally expect s comes first and you square it and you get s squared, right? But it kind of doesn't work that way in these definitions. In these definitions, the variance comes first, we call it s squared, and if you want to take the square root of it, then that's a really good plan, and we call that s. And so s here is the square root of 12, which works out to about 3.464. So what's the benefit? I know how to interpret this because it has the right units. And it actually makes sense in a much more interpretable way. So let's go through some unit examples. S is, let's just round this off to 3.5. So if these are plants' heights in inches, S squared is 12 square inches, and I don't know what sense to make of that, but S is 3.5 inches. And that's really comparable to the heights. What that's really saying here is the average height is 6, but a variability of about 3.5 inches is typical and normal. Now notice that some of the plants vary more than that. This is 4 inches taller. This is 5 inches shorter. So 3.5 inches is not the total possible variability, but it's a typical variability of all of these plants. If these are ages in years, then the variance will be in square years. I have no idea what it means, but the standard deviation will be 3.5 years, and it really will mean the right thing. It will mean that the children are 6 years old on average, but they tend to vary about 3.5 years older or younger than that. Yet again, if these are quiz scores, then the average quiz score is about 6 points, and quiz scores typically tend to vary above and below that average of 6 points by about 3.5 points. We could worry about maybe this quiz was too hard because the scores ended up a little bit low, but that's beside the point. So by taking the square root of the variance, we recover a value that we can actually interpret and make sense of because it has the right units. It has the same units as the data values themselves. And this is really important to us because this is the only thing that we really know how to interpret. So we get this value, and we shouldn't think of it as the total possible variability. It's not the whole range of variability. The standard deviation tells us how much variability above and below the mean is typical of the data values. Now, many of the data values might vary less than that. They might be right on the mean, or they might vary more than that. But 3.5 in this case is about the typical variability above and below the mean, and that's what the standard deviation is really designed to tell us. So the two most important measurements about any quantitative variable are, first of all, its mean, what is the average, and second, its standard deviation, what is the typical variability above and below the mean. And now you know how to calculate both.